So it will be fun watching Canvas give me the error messages going, that's a low points. I know it is. Put them in there. Yes. Yeah, I've seen that one. Most of my career so far, I felt like the meme of the dog sitting in the cafe that's burning down, and this is fine. I need to bring back out my shirt with the turtle on it that's surrounded by fire, and he's just in his shell going, I want to get the shirt with the T-Rex on it with a comet coming down. He goes, well, at least there's always tomorrow. Okay, so last time we talked about charging an RC circuit. We derived that equation. So I figured I could just say this time by similar arguments, we can also get to an equation for the discharging of the capacitor in an RC circuit. So, we talked about you have multiple switches. One switch you close, it charges the capacitor, and then you open that, the capacitor stays charged. The next switch you close is for the discharging of the capacitor and allowing electricity to run into the circuit. And so this is the equation that will actually calculate the discharge of that circuit. Now you notice I put the Greek letter tau in here this time. That's still your charging constant, R times C. And this is one of my new obsessions, putting medieval weaponry into pictures of animals playing. No, I didn't create that, but I found it and I was like, this is my new thing now. Oh yeah, no, it's good. But still, if you drop out of science to go to film school, I'd be fine. Well, I mean, here's I saw a video of a guy at a modern art exhibit, and he got real serious. He goes, I'm like, oh, for real? Are we starting that way? Okay. And he just ran, he had a marker in his hand, put it against the wall, and then ran, and then jumped on a trampoline, and then just made a mark on the wall like this. And everyone goes, oh, bravo. I'm like, are you freaking for it? Do what? Yeah. So I was just like, I'm like, if people were still producing works of art like they did in the Renaissance, I'd be all for it. But we don't. Because over the years we've accepted this mediocrity. Yeah, running, jumping, makes a mark on the wall with a marker. Everyone claps. I'm like, absolutely no, 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 no. This is why I drink. Like, that's why I had the day a couple of years ago, and I still want to thank all of our freaking biology students for actually learning something when I was having a bad day, and I said, I reject human, wish to return to monkey. And someone goes, it doesn't work that way. I'm a physicist. I don't know how it works. But yeah, there are days where I'm like, I really just want to reject this whole human thing. I want to go sit in a tree and eat a banana. I want to give up. So now let's see if we can solve a problem. Charging an RC circuit. Oh, so this one's fun. This RC circuit controls the intermittent setting on your windshield wipers. So your windshield wipers go down based off how you charge it. Once the capacitor is full, your windshield wipers go think, think. But you can, the amount of current you're sending in, you can change the charging time. So like you're just turning your little knob and it's either charging the capacitor slower or faster. And then your windshield wipers, once they have full charge, go thunk. So the EMF to charge this circuit is 12 volts. Let me find this problem. Okay. The wipers are triggered when the voltage across the 125 microfarad capacitor reaches 10 volts. Then the capacitor is quickly discharged and the cycle repeats because it takes all of the charge in the capacitor to make the windshield wipers do their thing. What resistance should be used in the charging circuit if the wipers are to operate once every 1.8 seconds? Actually a nice little engineering problem. Could you design this? Could you design a circuit with the proper resistance to accomplish the goal? So this is a set, I mean, your computers are much more advanced, but it's the same idea. You look at your motherboard, you see capacitors and resistors and inductors all over the place. They're all put in there to perform a specific task. Like for example, inductors are to help prevent current overload. The current goes into a coil of wire. That coil of wire produces a magnetic field, which then produces a back current. And so instead of the current being able to just go straight through and fry the system, it now has to fight against this magnetic field, which limits the current to the next part of the circuit. So how do you think? So let's look at solving this. Okay, so we're charged. So this is a charging question. Like we're charging the capacitor and the wipers. And again, you can say Q max or Q final. So we start here, and we're given a question with EMF. So remember, we can say that this let's see where. Okay, so then we're going to do Q over C. What does Q over C equal? The delta V of the capacitor, which is the 10 volts that you're after. And that's going to equal EMF. Okay, now you notice that your R, you want to know what kind of resistance this needs. You notice that your R is buried inside of an exponential. I want you to take a couple of minutes and see if you can solve for that R. How do you get something out of the inside of an exponential? Okay. For those of you who are more like medical people, how let's just go back to like pKa. If the pKa is the negative logarithm of the Ka, how do I get the K? How do I extract the Ka from the pKa? Well, so for pKa, it's log base 10. Right, how do you do that? So like this is log base E. How do I, well, it's already in an exponent. The E is the exponent. Yeah. If I take the natural log of the E, then I just get what's in the I get what's in the exponent back. Try to use a chemistry reference because I thought more people knew chemistry. Oh, okay. You have like the LN button and above it the E button. Okay. Well, but see, it's already in the E. You need the LN button. Kind of a mean equation. See if you can get to. As your denominator, C natural log of 1 minus delta V over E, and then the time on top. See if you can get there. Is there a special thing I have to turn on? Those of you who erase just by scribbling, mine won't do that. Is there like a special setting, huh? Yeah, notability. It probably is. Huh? Yeah, I've just seen people doing it lately. I'm like, I want to do that. Did you get something in like kilo ohms? Yep. See, this is why you can't go up. Yeah, yeah. I'm sorry. I don't ever want to lose my job. However, for the good of the world, if you drop out of science to become a film student, I will find you, chloroform you, and drag you back to science classes. I just, I can't allow this. I would be willing to lose my job to get you back into science classes. We can't. Mm-mm. Okay, so let's see. What can we do? Can multiply the EMF into the whole thing. Okay. And then we have EMF E minus T over RC. That is going to equal all right. So then which how do I break up fractions? Yeah, since everything on the top has the same denominator, I can do E over E. Yeah, it becomes 1. Okay, now we have to take the natural log of both sides. When I take the natural log of the left side, I get let's see, negative T over RC equals the natural log alrighty. And then I can start multiplying through, get 1 over R. So the C is going to multiply through. I'm going to get a negative sign, C. And that's all going to be over time. But this is the inverse. So then I need to do 1 over everything. So then my R is going to equal so see, if I was to ask that on a homework, that's not that much of a derivation. It's just algebra. Well, You guys have made it this far. You've been able to pretend you know how to do algebra pretty well. And like I always say, if the problem on the physics homework's too hard, just fake it till you make it. Just in the future, don't lie on job applications. That can get you in trouble. You get the job, and then you're expected to perform a task going, I don't know how to do that. But but if you think you can learn how to do it and get away with it, I don't know. It's still risky because you come in expected to have skills, and you're like, I don't have those skills. What do I do? After 2 weeks, going, I didn't think I'd get this far. so so then our R value gonna be a negative. So what our C 125 times 10 to the negative 6 farads. Natural log 1 minus 10 volts over 12 volts. And the charging time is 1.8 seconds. And we get 8,036.8 ohms or 8.04 kilo ohms. We got this? Because it is time to start having fun with magnetism. Okay, so yeah, we're going to go back to some harder math for just a little bit. And then once we're through magnetism, we'll be getting on to optics, which is, well, now I say it's just geometry. It is like some people are going to do, yeah, I can do geometry. Is anyone going, oh, shoot? A little bit? Okay. We're going to have to bring back out our sophomore in high school geometry, and we'll learn optics. Got a really good idea for a problem once we get to optics. It involves light diffraction by the human eye. It took me coming here to realize that a DO is not a doctor of optometry. I always thought that was, I don't even really know what obstetrics is, but what? No, I was serious. I didn't know, like people kept saying, I'm going to be a DO. And I'm like, an optometrist? That was the joke. I had no idea. I was like, you're going to have to tell me. I build particle accelerators. I don't. That's why I always hate the science professors who are like, yeah, I'm an expert of all areas of science. So you most certainly are not. If you put me in a bio lab and someone goes, what do you see through the microscope? I'm like, goo, green goo. Uh-huh. What class was that? OChem. Yeah, that sounds like OChem. Smelly and brown goo. Biology is green goo. If you're lucky in biochem, you actually get crystals, but they're amino acids. No. Now, magnetism. Now, I put this on here. I want to see if anyone knows what it is. And it kind of looks like Tony Stark's arc reactor, but this is an actual real thing. You see the beams of particles going round and round and round. That's the magnetic field causing them. Kind of, but it has a different purpose. It's an example as to why we can't accept mediocrity anymore. We have to strive for greatness. Because this is from a group of people who strove for greatness and they're beating the pants off us. This is a model of the fusion reactor in South Korea. They're using plasma, magnetic field, and particle acceleration to jumpstart nuclear fusion. Very, very likely soul would be a piece of charcoal. I don't know if it's in salt. Where it's at. Kind of like one of our largest particle accelerators is right outside of Chicago. My favorite national lab is just outside Knoxville, Tennessee, which is just a really nice place to live. Houses probably the United States' most powerful computer. We're trying to find gold. Yeah. Get more protons in there. Yeah. So so this is a mock-up of the fusion generator. You can actually Google the South Korean fusion reactor. It's pretty cool. And they get this nice, pretty glow out of the inside, but you know that glow would turn you into dust within seconds. So magnetic fields. The lowest order magnetic system is a dipole. So you know how we've had electric systems where you've had like point charges and they radiated an electric field? You cannot have that with magnetics. You have to at least have a dipole. The magnetic field is going to go out of north and into south. So make sure you're noting which way the magnetic field flows. It's going to be a vector quantity. So you want to start paying attention that B is going to be your magnetic field. So just like E was your electric field, B is going to be your magnetic field. It's a little less intuitive. Like, why didn't they just use M? I don't know. They didn't. You'd have to ask Maxwell and Faraday. Faraday did the experimentation, Maxwell did the math. All right, so your field lines, just like with electricity, they can match up. You can have attractive fields and repulsive fields. Now these fields you could actually play with. Remember when you were a kid and you tried to put the magnets together and they wouldn't go? That's because you're like putting either two north poles or two south poles together. And this is the one that usually makes people lose their minds. Well, the North Pole is actually the South Pole, and the South Pole is the North Pole, and the South Pole doesn't line up with the North Pole, and the North Pole doesn't line up with the South Pole. So humans to think of that one. So I always love that example because every semester there's a little similar. Even I don't really know that. I'm not really. So the magnetic North Pole is actually at what we call the geographical South Pole. And it just has to do with how the needles in your compass actually line up with the field line. So they're going to go with your compass will line up in the direction of the field. And so it points what we call geographical north. But you also notice there how the geographical and magnetic poles aren't right on top of each other. Now that could be problematic, which was why, what was that, last year? Who remembers people going, I'm going to go out and look at the northern lights, they're so pretty. Do you remember that? Yeah, and when people ask me, like, don't you think they're pretty? I said, no, I think they're freaking terrifying. And someone said, why? I go, because you see this here? That means that some bitch was rocking. There will come a time when the magnetic north and south pole will switch. Will it be an extinction level event? Probably not. However, it will cause problems like all of your little fancy little tech devices. They'll die. And you will have to get new ones. Wi-Fi will die. All the signals that we depend on will be like at least temporarily erased. Like it's
It actually got.
most computers, which is computer room, you just shut it. I mean, it's not something that like will affect your body, the person. But it can affect other things on the planet. Okay, so then I think that's the question of what causes the magnetic field. So, okay, so, and we'll talk about this a little bit. So let's just put it this way. You have a coil of wire. You send a current through it, get charged particles spinning. Those charged particles moving create a magnetic field. How do you think the Earth does this? The core. The molten metal in the core of the planet spinning causes a magnetic field. Now, you have to ask Embark. I'm not exactly sure what the core is doing that causes the magnetic poles to shift. Theoretically, I mean, it would almost like, I don't know if this is what happens, but it almost be like a reverse of the current. But we are. Now, the question is, what will get us first, the poles switching or Yellowstone going coming?
The poles.
Possibly. No, like every couple hundred millennia or more, million years, we are kind of like that past due stage. So, yeah, so when people are going, the Northern Lights are so pretty, you're like, that's how humanity dies, it smiles and cries. It just.
What did you do about it?
Nothing, absolutely nothing, but you can at least realize what might be happening. But yeah, so you're getting like a rocking of the Earth's magnetic poles. And a number of things cause that. The Northern Lights is plasma discharge when solar wind hits the apex of that magnetic field. Because you see how it goes down to the top of the planet, and you get this little like dimple, that little dip there. So when the solar wind glances off at that angle around that apex, you get a plasma discharge. So not only were you seeing kind of like a rocking of the magnetic field of the Earth, you were also seeing particles from the sun discharging on this protective barrier that we absolutely depend on. So no, I wasn't real fond of it when that was happening. And then I had someone go, yeah, well, nobody knows that other stuff, so just enjoy it. I'm like, it's not my fault you don't read. Now, to kind of get an idea of just how massive magnetic fields can be, Earth's magnetic field does, yes, it blocks off particles coming from the sun. Now, you see over here, it gets nice and compressed. That's because it's being pushed off by those particles. In reality, this electromagnetic field is essentially like a version of like sci-fi shielding. So it gets pushed on by the solar wind, but over here it's allowed to stretch out. Where it's not being pushed on, the magnetic field of the Earth stretches out to about 3.9 million miles. So we're talking about strength, not on like this. It's like, oh, we're just talking about this little bitty thing you can do in lab. No, we're talking about cosmic scales. Actually, Jupiter's magnetic field reaches us. It's not strong enough to protect us. So magnetic fields are some of the most powerful things in the entire universe. Which is the fun thing about what they're discovering about quantum gravity. It's starting to look like that the electric and magnetic system is actually a mirror of the mass gravity system. Look at the math. There's perfectly symmetric. If you start doing like for example, the area study called quantum electrodynamics, you will see equations for electricity and magnetism at the quantum level that mirror Einstein's relativistic equations. So it almost looks like the Higgs boson and the photon perform very similar functions, this gravitational mass system or electromagnetic system. Now, magnetic force on a point charge. So if we look at this, QED sine theta, okay? You've seen an equation like that before. What do you think this is? If you were to write this in its vector format, what does it look like? It's a cross product. So, yes. So you get the vector product. Now, the way you're looking at this, so again, we're going to be bringing back in right-hand rules. And I know a lot of people hated these, but you got to figure out the one that works for you so you can get the so that you can get the proper direction of the force. Because again, if I have a magnetic field coming straight at you and a charged particle enters that field, the charged particle is forced that way. Yeah. It actually demonstrates quite well experimentally going back to the orthogonality of the space-time that puts the magnetic negative. They propagate together, but their spatial realities are shifted by 90 degrees. So, now the way you can really think about this is so like this magnetic force here will be coming out at you. You see if you place your fingers in the direction of the velocity and cross them into B, like rotate them into B, and some goes out that way. There's a number of ways you can do this. Again, so let's say I can put my fingers in the way of velocity, have B point out my palm, my thumb points out that way. That's another way to do it. Want to make sure we understand the units of magnetism down at the bottom here. So we have force over Q times B, or newtons over Coulomb times meters per second. Newtons over amps times meters. They all equal T. What do you think T is? Nope. This is a unit. It's the SI unit for magnitude. Okay. I will tell you it's the name of a very famous scientist from a lot of really cool things. But most people look at me and go, you know what to call it. That's all. So the magnetic unit is Tesla. So a couple more rules for your right hand rule. I prefer the one just to like wrap your fingers and your thumb goes in the direction of the field or the force. Again, we go back to like rotating wheels on your car. If you have two cars that bump while the wheels are going, you fire off of each other. That's because the force vector is actually going straight out of the wheel. It's a cross product. The torque of the wheel provides a force vector straight out. So energy transfer in a torque system happens at 90 degrees to the system. Same kind of idea here. Also remember, if we're working with cross products, that they are not commutative. That's one of the mathematical rules. So for example, I can't just do B cross V and have it be the same thing. So cross products are anti-commutative. If we get to a point where we actually need to formulate the cross product, we'll do that. Just know that most of the time, so like your V cross V will break down into V, the magnitude, V times V sine theta. Because I really don't think I'm allowed to have you guys do matrix math in here, so we will leave the linear algebra out of it. Yeah, we're kind of done. I want you, I do want you to start wrapping your mind around this over break. You see the dots and the crosses? We're now gonna have to represent vectors in multiple dimensions. We can draw them in the page and have X and Y. You're not gonna have to picture them either going into the page or coming out of the page. Your dots are going to be going in, your X's will be coming out. So it's just gonna be a new way of representing things.